All right, we're looking at tape 415, part 1. This is the application of derivatives, and we're going to look at maximum and minimum, how to calculate those, and points of inflection also. So let's look at the graph there on the right of your page, and let's kind of read through what it says in the notes. It says, since the derivative of a function is the slope of the line that is tangent to the curve. Wait a minute now. So the derivative of whatever this function is, it represents the blue graph line. The derivative of that, if I plugged in this x value right here, then I would get what the slope of this tangent line is. If I came along and plugged the x in here, then it would give me the slope of this tangent line. The x here would be the slope of the tangent line. The x value here would give me the slope of the tangent line. So the first derivative gives us slope of the tangent line to the curve at that value of x. Well, now wait a minute, look. Then that means, what's the slope of that line? That slope is 0. And the slope of this line is 0. So we can find minimum points on a curve or maximum points on a curve if we take the first derivative and set it equal to 0. If we take the first derivative and set it equal to 0, then that gives us the x value. When we solve that for x, then it tells us this x value for when the curve is at a maximum. It gives us the x value for when the curve is a minimum. Now, how do we tell whether it's a max minimum if we don't have the graph there? Well, look here. What is the slope of this tangent line on that side of this x value? Well, that's positive something. And then on this side, the slope is negative. Therefore, if the slope changes from positive to negative about a point that makes the first derivative 0, we have found a maximum. If the slope about a point that makes the first derivative equal to 0 is negative on the left and positive on the right, we found a minimum. Aha! Now, keep that in mind as we read through all of this top part of the first page. It says if we put a value in for x in the derivative that makes the derivative equal to 0, then we have found a point like B or D, maybe, okay? The point B is called a maximum, and it's also called a local maximum because this curve keeps on going up, so that's not the highest point of the curve. And this would be a local minimum because it's not the lowest point on the curve. Now, if this curve did not come back down and this was the lowest point of the entire curve, then this would be called a global minimum or an absolute minimum. All right, now what I want to do is to read what is in the small lettering on that first page. It says this: if the value of x on the left of the critical value. Now the critical value is whatever makes the first derivative equal to 0, which would be this. This would be the critical value. This would be a critical value. Okay, this point right here could possibly be a critical value. All right. Now let's say that all three are critical values. Now it says, if the value of x on the left of the critical value, I'll pick some number here on the left, is placed in the first derivative, and it gives a positive value, a positive slope, and the value on the right of this point gives us a negative value in the first derivative, then therefore this is called a maximum. And the next paragraph says if the value on the left gives us a negative and the value on the right gives us a positive, therefore this is a minimum. And that's what makes maximum minimums. You see, if we put this x value in the first derivative and we get 0, that means this is a critical value. We don't know yet what it is. It's a critical value. Then we check on both sides. If it's negative slope on that side, positive slope on that side, In other words, for the first derivative, for this x value right here is negative, and for this x value is positive, therefore this is a minimum. What would happen on a point like this, see, you get on this side you get a negative slope, and on this side you get a negative slope. It does not change sign. Therefore, this critical value is not a maximum or minimum. A maximum or minimum says that the slope on each side of this must be different. The slope must change as it goes through. See, this slope is positive, 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 0, negative, negative, negative. So it changes here, therefore it's a maximum. It changes here from negative to positive, therefore it's a minimum. All right, let's now look at example 1. Okay, y is equal to x squared plus 6x. All right, step 1. Take the first derivative, set it equal to 0. And why set it equal to 0? Because we're saying this is slope, so we're going to make the slope 0 and find what x value the slope is equal to 0. In solving that, we get a minus 3. Now, I like for my students to leave a line here on your paper, where you have a lined paper. Leave a space right here. And we're going to write above this whether it's a maximum or a minimum. All right, so we have a minus 3. Now we fill in this. This comes from the original equation. The original equation. You always find the y from the original equation. So when we put a minus 3 in the original equation, we get a minus 9. All right, to determine whether this is a maximum or a minimum, we check on both sides of this in the first derivative, in the slope. So if we put a minus 4 in the first derivative, 2 times a minus 4 is a minus 8, plus 6 is negative. So that means it's a negative slope on that side of a minus 3. If I put a minus 2, I'm looking on this side of the minus 3. If I put a minus 2 in the first derivative, that gives us a minus 4 plus 6 is positive. This is a positive. That means now, graphically, let's just kind of look at the sketch right here. That means over here at minus 3, minus 9. On this side of minus 3, we have a negative slope. And on this side of a minus 3, we have a positive slope. Therefore, the curve has to come like that. Therefore, this is a minimum. And that's how you work max and minimum. Let's go back over it and over it and over it. You take the first derivative, set it equal to 0, solve for x. Then you check on both sides of that value. If it changes negative, positive, it's a minimum. If it was positive, negative, it would be a maximum. All right? And underneath this then, we take the second derivative. Second derivative is equal to 2. Now there's a shortcut rule for determining this. And I'm going to say this each time, but we're going to work this concept also, plus minus. Is if I take a minus 3 and put it in for x down here, and it's positive, then it's a minimum. Sure enough, this is positive. So therefore, this is a minimum. If you take this number and put it in the second derivative and it comes out to be negative, it's a maximum. That's a shortcut method. It doesn't work all the time. Therefore, we have to know this process of plus, minus, minus, plus. All right, let's look at the problem graphically. To sketch this, all right, we'll make up some points. Now remember, y is equal to x squared plus 6x. So if x is 0, y is 0. There's 1 point. If x is 1, y is 7. If x is a minus 1, y is a minus 5. If x is a minus 2, y is a minus 8. If x is a minus 3, oh, that's the point we found. is a minus 9. A minus 4, 8. And so what we get is a curve like this, showing that this is a minimum at minus 3, minus 9. And sure enough, our work's right. Slopes over here are negative. Slopes over here are positive. The slope right here is 0. That's why we set the first derivative equal to 0. All right, let's now look at example 2. Okay, example 2 in your notes. So we take the first derivative, 5x to the 4th minus 15x squared minus 20. Set it equal to 0. And solve. Well, let's see. Let's factor out 5. And then this keeps factoring. X squared minus 4 and x squared plus 1. Now we solve for x. Now this is supposed to be from your algebra. If we set that equal to 0 and solve for x, we can't get anything. Move that across, it'd be square root of minus 1. So those are no real positive roots. Set this equal to 0, move the 4 across, take the square root, get a plus and minus 2. I'll leave a space here, so we get a minus 2 and a plus 2. Okay. Now plugging a minus 2 and plus 2 in the original problems, we get 114 and minus 46 for the y values. All right, now let's determine maximum minimum. So we check on both sides. So if I put a minus 3 on this side of a minus 2, if I put a minus 3 in the first derivative, we'll just use this step right here. It's easiest. Forget about being equal to 0. We just want to know whether this is positive or negative. So if I put a minus 3 in here, that's positive 9. That's positive. Squared is positive, so that's positive on this side. If I put a minus 1 in here, if I put a minus 1 here, it's negative. And positive, that's always positive. So that's negative, so this changes from a positive to a negative. Positive slope to a negative slope, therefore maximum. Look at that, it's a negative slope, positive slope. So therefore, positive, negative, therefore it's a maximum. Now let's come over here and look at for this one. If I check a number on that side of 2, which would be a plus 1, I put a plus 1 in here, that's negative. That's always positive, so that's negative. If I put a 3 in here, this becomes positive, and therefore this is a minimum. If it changes sign, plus to minus, maximum, changes from negative to positive, minimum. All right, so that gives us those values. Now let's come down and take the second derivative. Second derivative. Now listen to this. I want you to look at this step right here. On the second derivative, you can take the derivative of this part. You can factor out any constant. Not a minus, not a minus, not a minus. You can factor out any constant, get it out of the way, and go take the derivative of this, and it still works for you. So the derivative of that is 4x cubed minus 6x. Setting that equal to 0, we can factor out a 2x. That leaves us a 2x minus 3, and therefore, I'm going to come over here and finish this up. Therefore, we have 0 and 3/2. No, wait a minute. I got a mistake. Let's go back down here and look. My mistake here. This is x cubed, so that's an x squared. That's an x squared. So when I set that equal to 0 and solve, I get plus and minus square root. Now let's come back up here then and write this. And so what we have is minus the square root of 3/2, 0, and positive the square root of 3/2. All right? Now, let's go back over to where we looked at max and minimum and look at the shortcut. If we go put a minus 2 in the second derivative, that would be a minus 8, a minus 32, plus 12 is negative. If the second derivative is negative for this value of x, then it's a maximum. If I put a plus 2 in here, it will be a positive 8, positive 32, minus 12 is positive, therefore it's a minimum. That's the shortcut method. But don't forget, when it fails, for instance, if I plug this in and got a 0 in here, then it fails, and I must go back and check on both sides. So you need to know both methods. All right, now back over here, let me rewrite the second derivative up here on top of this. And let's check for points of inflection. Points of inflection. So if I check on that side of this, okay, that's a square root of 1.5, and the square root of 1.5 is like 1.2. So if I had a minus 2 in here, I would get negative. And if I put a minus 1 in here, I would get positive. So it does change signs. Therefore, it is an inflection point. If it changes signs, it is an inflection point. If it changes signs, all right, then this would be positive, negative, so it's an inflection point. And this would be negative, positive, so it's an inflection point. So now let's see how we do this then. Here's the sketch of this. All right, at a minus 2, over here at minus 2, and we can't come down here 114 spaces, so that's why you label things. You will call this whatever it is, all right? No, I'm sorry, that's a positive, excuse me. It's minus 2, positive 114. So we'll label it minus 2, positive 114. And then over here at plus 2, it's a minus 46. So we'll label it at 2 minus 46. All right, so we got that. Now we put these inflection points in here. A minus 1.2, okay, is somewhere in here, whatever the y value is. 0 is a plus 2, somewhere in there. This would be a plus 2. And then the square root of 2 in there would be somewhere in here. Now watch. This is a maximum. So the curve comes here and comes back down. Changes directions, changes concavity downward to concavity upward. And then it changes concavity again. And then it changes one more time. And so that's the sketch, okay? Here we have a maximum. Here we have a point of inflection, point of inflection, point of inflection, minimum, and that's the curve. Okay, let's look now at example 3. Okay, example 3 is y is equal to x to the 4th plus 4x cubed plus 14. All right, first derivative. Set it equal to 0. And I'm going to do it all in one step. Set it equals 0 and factor out. I can factor out a 4, x squared. That leaves me an x plus 3. Okay, set each factor equal to 0. Setting this equal to 0, we get a negative 3. And setting this equal to 0, we get 0. Now, you'll be very wise if you'll always put these in ascending order. I'll show you why. It's very important. Another example. Put these in ascending order. All right, we want to know, well, let's see. Let's go ahead and get the second derivative while we're here. Second derivative of right here. So if we take the second derivative at this step, we would have then 12x squared plus 24x. Setting that equal to 0 and solving, we get x. So therefore we have minus 2 and 0. Ooh, wait, notice that we have 0 both places now. We have it for maximum, minimum, what's called critical value, and we also have it down here at a possible point of inflection. It can never be both. It can never be both. It's got to be one or the other, and sometimes neither one. That's why we must check on both sides and all these other rules. All right, so let's go back now at this step and look at these bottom steps. Okay, we want to check on, well, let's use a shortcut method. If I put the -3 in the second derivative, a -3 in the second derivative, this would be negative times negative, therefore that's positive, therefore this is a minimum. Shortcut method. Place this value that you found from the first derivative in the second derivative. If it gives you positive, minimum. If it gives you negative, maximum. But look right here. If I put the 0 in the second derivative, I get 0 times 2, which is 0. Test fails. That's not positive, that's not negative. So therefore I must go back up here and check on both sides in the first derivative. Determine whether this is a maximum minimum. I must check on both sides of this in the first derivative. So if I put a -1 up here, I get a positive. Squared is a positive, so that's a positive. If I put a +1 up here, I get a positive. Positive. It does not change signs. It does not change signs. Therefore, it is not a maximum minimum. That's why we have to do all this method. You can use a shortcut method, but if the shortcut method fails, if this is a 0 down here, then you must come back in the first derivative and check on both sides. If it does not change signs, then you mark it out, and you better mark it out to make sure you don't say that's a maximum minimum. So we only have the point -3 -13. Now the -13 comes from the original equation. All right, now looking down here for these 2 points at -2, and 0, 14, let's check on both sides in the second derivative. Check on both sides. If I put a -3 here, that's negative, times a negative, that's positive. If I put a -1 here, that's positive, minus, that's negative. So therefore this is an inflection point. All right, if I come over here and put a -1 in here, I get negative. If I put a +1 in there, I get positive. So it does change signs. So it is an inflection point. Now we're not going to worry too much right now whether this is minus plus or plus minus. I'll talk about that a little later. But if it does change signs, it is an inflection point. All right, well, let's see what this does when we try to sketch this then. All right, so we come over here, 1, 2, 3, -3, -13. And that's a minimum, so the curve comes like that. All right, then at -2, -2, we have an inflection point. And at 0, 14, we have an inflection point. Now, watch. So therefore, this is a minimum. Comes up here. That's concave upward. Concave upward. Hey, let's go over and look right here. On that side of a -2, it's positive, concave upward. On this side, it's negative, concave downward. Go back and look at the graph. So on this side of the -2, it's concave downward. So the curve concaves downward. All right, then at the 0, 14, on this side it's negative, it's concave downward. On this side it's positive, concave upward. So that's what the sketch looks like. All right, now let's look at example 4. All right, let's take step 1, take the derivative. So the derivative of this is product rule, product rule. So we'll write, let's see, the first one down, take the derivative of this. So it's 3 times 1 minus x squared times the derivative of the inside, plus writing 1 minus x cubed down and take the derivative of x, which is 1, product rule. Now, set that equal to 0 and solve, all right? So let's set it equal to 0, and what's a common factor? Common factor is 1 minus x squared, okay? And what else? That's it, I guess, isn't it? So what does that leave us? Over here it leaves us a minus 3x, and over here it leaves us 1 minus x. So let's take another line here, and that gives us 1 minus x squared, and this gives us 1 minus 4x, doesn't it? Okay, removing parentheses here, we get 1 minus 4x. Okay, then that tells us what? This would be 1, this would be 1/4. So putting them in order. So these are the critical values. Critical values, therefore we have to determine whether they're maximum, minimum, or not. Either one. Okay, well, let's go ahead and take the second derivative. Taking the second derivative, now to get the second derivative, we would take it from here, writing this one down, take the derivative of that, and write that down, take the derivative of that. And then on the tape, let me just show you, that would then be 1 minus x and minus 6 plus 12x. All right? So therefore, these points then would be what? 1/2 and 1. So this would be 1/2 and 1. Again, notice we have both the 1 and the maximum, minimum, and points inflection area. So we're going to have to worry about checking on both sides on those. Let's plug in the values here. This will be 27 over 256, and this would be 0, and this would be 0, and 1/2 is 1/16. These values come from the original equation. Go back and plug in the numbers. Now let's get after it. Shortcut method. Put the 1/4 in the second derivative. If I put a 1/4 here, I get positive. If I put a 1/4 here, I get negative. 1/4 times that's 3. I get a negative, positive, that's negative. Therefore, this is what? Maximum. If I put a 1 in here, I get 0. Test fails. So I must go back and check in the first derivative on both sides. Now, what is a number on that side of 1 that I can check? And some of you may say 0, and you're wrong. That's why you must put these in. You cannot go across this number. For instance, if we had numbers to check, like a -3, a -2, and a -1, when I check on this side of a -2, I can't use that one. So I must stay between those values. And that's why you have to put these in ascending order. So when I check on that side of 1, then I'll check a 1/2. Okay? So I'll check a 1/2. So if I put a 1/2 in here, square it, that's positive. If I put a 1/2 in here, it's a -2. 1 minus 2 is negative. So that's negative. All right, on this side of a 1, if I put a 2 in here, that's negative. That's always positive. It's negative. Does not change signs. Therefore, you mark it out. It is not a maximum. Now, stop for a moment and watch this little trick. Anytime any one of these roots comes from an even power, if that power in the first derivative is an even power for that root, then it will not be a maximum. It will not change signs. It'll either be both minuses or both pluses. If the root that you get right here comes from an even powered multiple root up here, then it will not be a maximum. And most of the time it will be a point of inflection. Because in the next derivative this will drop to an odd power, as you notice down here. It drops to an odd power. Now if it's an odd power, it will change signs. All right, so there we have check points inflections. All right, coming down here, checking on this side of 1/2, we'll put a 0 in here, that's positive. -6, that's negative, it changes. If I put what did I try on this side of 1/2, I can't use 1, So I got to try 3/4. I put a 3/4 in here, that's negative. Put a 3/4 here, that's 9 positive. So it does change signs, so it is an inflection point. Now checking 1, it's positive on this side. If I put a 2 in here, that's positive, negative, so it does change signs, so it is a point of inflection. Now graphically, here's what that looks like. At when x is 0, y is 0, when x is 1, when x is 1/4, when x is 1/2, and when x is 1. Remember, at 1/4, this is a 1/4, it's a maximum, changes, that's a point of inflection, so it changes concavity, and then it changes concavity again. So these are points of inflections, and this is a maximum. All right, now let's look at the next example. All right, the next example now is showing you all the different cases where some of these tests fail and all this other stuff. So watch. First derivative. Taking the first derivative, which is a positive 1/3 x to the minus 2/3, setting that equal to 0. Well, before we set it equal to 0, while we're setting it, let's do the algebra. The 1 stays on top, 3 is on the bottom, and this is moved down x to the 2/3. Now, here's a new rule. The rule is we take the first derivative, set it equal to 0, solve for x. Well, there's no x up here to solve for. So here's a new rule. Anything that makes the denominator 0 is a possible maximum or minimum or point of inflection also. So anything that makes the denominator 0 is a critical value to look at. So what makes this 0? Well, it's 0. All right, so when x is 0, y is 0. Now let's take the second derivative. Second derivative would be a minus 2 over 9x to the 5/3. And so what makes the denominator 0? 0, 0. Now notice again, we have 0 in both places. It can't be both of them. Sometimes it's not either one. So let's check it out. All right, so let's check on both sides for this one. In the first derivative, if I put a minus 1 in here, the cube root of a minus 1 is a minus 1 squared is a positive. Into a positive is positive. Now on this side of 0, if I put a plus 1 in there, the cube root of plus 1 is 1, squared is positive, into a positive is a positive. Does not change signs, so we mark it out. So now let's go down to the second derivative and check. If I put a minus 1 in here, the cube root of a minus 1 is a negative 1, raised to the 5th power is negative, divided into negative is positive. If I put a plus 1 in here, cube root of a plus 1 is 1, raised to the 5th power is 1, into a negative is negative. It does change signs, therefore it is a point of inflection. Okay, so here's one where you have no maximum, only a point of inflection. Let's look at what that means graphically. Again, the curve is y is equal to x to the 1/3. Okay, and we're checking 0, 0. And let's see, the 0, 0 was positive this side, negative this side. So that means on this side of 0, it's positive. That's concave upward. So it's concave upward. And on this side, it's concave downward. So that's one way of using the concavity of the second derivative. Another way, an easy way, is to plot points. If x is 0, y is 0. If x is 8, what is the cube root of 8? When x is way out here, y is just up 2. So it tells us that. When it's a minus 8, it's a minus 2. So plot a few points also. All right, let's look at example 6. Taking the first derivative, which is 2/3, x to the minus 1/3. Okay, set that equal to 0. That's positive 2 over 3 times x to the 1/3. And here again we have that 0, 0 thing. Taking the second derivative, we will have a minus 2 over 9x to the 4/3. All right, and so we have that 0 thing again, all zeros. Now again, let's look at these 4 lines right here and check the positive, negative bit. Here for 0, checking in the first derivative, I put a minus 1 in there. The cube root of a minus 1 is a minus 1. Raised to the first power is a minus 1, and a positive is negative. If I put a plus 1 in here, it's positive. It does change signs. Negative, positive, negative slope, positive slope, therefore says minimum. Now, it can't be both. If it's a minimum up here, it's not going to be anything down here. It will not be a point of inflection. But we better double check to make sure our work checks out. So down here, checking a minus 1. Cube root of a minus 1 is a minus 1. Raised to an even power is positive, so it's negative. Put a plus 1 in there, it's negative. It does not change sign, so we mark it out. Now graphically, what happens is this. Okay, we have a minimum at 0, 0. So therefore the curve must look like something like this. Well, now wait a minute now. Look. The second derivative says it's a concave downward. It's negative concave. That's not right. That doesn't work. So what happens is this is where you have to watch for your concavity and plot points. What happens is it looks like that. It's concave downward, negative. It's concave downward. That's a minimum. See, that's why you have to put all this in here together. Plot points. If you come in here and put an 8, you get 4. If you put a minus 8, you get plus 4. Therefore, this concave downward, that's a minimum point. All right, let's look now at example 7. Okay, taking the first derivative, 3x squared plus 6x plus 3, set it equal to 0. Factor out of 3, we get x squared plus 2x plus 1. Okay, factoring that, we get x plus 1 squared. So setting that equal to 0 and solving, no. Even power. It's not going to be. You check on both sides of that. You put a minus 2 in here, it's still squared, it's positive. You put a plus number in here, it's squared, it's still a positive. So it's going to be positive. Even power is not going to be 1. So let's go take the second derivative. Second derivative is 2x plus 2. And therefore, setting that equal to 0, we have a minus 1. Now checking on both sides of this, put a minus 2 in there, that's negative. Put a 0 in there, that's positive. Changes sign. So it is an inflection point. And it's concave downward, concave upward. All right? Let's go back to the original problem. I want you to see something all the way down. The original problem, what this was, is that can be factored and changed into x plus 1 cubed. So the derivative of that is 3x plus 1 squared. Look at that, same thing. And then the derivative of that is 6x plus 1, which is still the same. So therefore, x minus 1 is a point of inflection. So let's look at what it means graphically. All right, so graphically, what do we have here? When x is a minus 1, okay, point of inflection, and it says it's on this side of a minus 1, it's concave downward. So that must mean what? Something like this? Concave downward. Then on this side, it's concave upward. So at minus 1, we have a point of inflection. All right, now let's look at example 8. First derivative, set it equals 0. So it's negative 1 over 3 times x to the 2/3. Second derivative. Second derivative would be positive 2 over 9x to the 5/3. 0, 0. Now here we got all that 0, 0 business again. No, wait a minute. Wait just a minute. Let's watch something on this one. All right? Now, let's go back up here and check on both sides. So put a minus in here, that's positive, so that's negative. Put a positive in here, it's negative. Doesn't change signs, so we mark it out. So we go down here. If we put a minus 1 in here, we get negative. If we get a plus 1 in here, it looks positive. So it looks like a point of inflection. No, no, no. And here's the reason why. The y value doesn't exist. The y value doesn't exist when x is equal to 0. So here's a case where you can get positive, negative, changing signs, either here or here, but it's not point of inflection or it's not a maximum because the y value doesn't exist. Look back at the original problem. If I go back up here, this original problem is 1 over the cube root of x. If I put a 0 for x, the original y value is not possible. All right, that's why I put this example in here to show that sometimes all these tests work out, but you better not forget this idea. Go find your y value before you get started, because it's possible that it makes the original problem not possible. All right, let's look at example 9. Okay, taking the first derivative, set it equals 0. We'll do it all at one step. Would be 4x cubed minus 24x squared plus 44x minus 24. Common factor there is 4, so we'll factor out x cubed. Factor out of 4 leaves me x cubed, 6x squared plus 11x minus 6. Now this problem you must solve with synthetic division if you have to work things with pencil and paper. Now if you have a TI 55 or some other, 85, I'm sorry, some other calculator, put that in, find the roots, and the roots are 1, 2, 3. So therefore this is 0, 4 times x minus 1, x minus 2, and x minus 3. Therefore we check 1, 2, 3. So here's where you have to check on both sides, and you got to watch. When I'm checking on this side of 1, I better use 1.5. 1.5, 2.5, 2.5, and then any number I want to over here. All right, second derivative. Second derivative would be 3x squared minus 12x plus 11. Now the reason I put this one in here is to say, hey, that doesn't factor, so you got to use the quadratic formula. So the quadratic formula says x is equal to minus 12 minus b plus or minus square root of this squared minus 4 times a times c all over 2 times a. And so what happens is you get the two answers of 6 plus and minus the square root of 3 over 3 and 6 plus, and so you get those 2 points. Now look what happens. The square root of 3 is 1.732. From that is about 4.3 divided by 3 is 1 point something. Sure enough, it's somewhere between these 2 points. This is 6 plus 1.73, which is 7.7. Divide that by 3, you get 2 point something, which again is in between here. So these are probably max minimums and the points of inflection between them. Well, let's check everything out now. All right, here we go. If I put a 1 in the second derivative, putting a 1 in the second derivative, it would be a positive 3 minus 12, which would be a minus 9, plus, that's positive. Therefore, this is a minimum. If I put a 2 in there, this would be 12 minus 24 would be a minus 12, plus 11 is negative. Therefore, this is a maximum. And if I put a 3 in there, that would be 27 minus 36, which is a minus 9, plus 11 is a plus. Therefore, this is a minimum. And then checking on both sides down here, if I put a number in here and check, it does change signs, so it is a point of inflection. These are points of inflections. So let's look at what it means sketching wise, all right? Now for the minus 1, we get a minus 9. So for minus 1, we get a minus 9. Okay, minus 1, minus 9. For the plus, I'm sorry, not a minus 1. Excuse me. It's a plus 1. For plus 1, we get a minus 9. Okay. So 1 minus 9. And for the 2, we get minus 8. And for the 3, we get minus 9. So what we have is, well, wait a minute. We had a minimum, and then we have a maximum. Concave downward. Right in here is that 6 minus the square root of 3 over 3. Right in here, these are the 2 points of inflection. This is that 6 plus the square root of 3 over 3. So therefore, minimum, minimum, maximum, points of inflection. All right, let's look now at the last example. Example 10, taking the first derivative, all right? Set it equals 0. Write the first one down. The derivative of this is 0. Sigma x, the graph of that, is like this. What is the slope of this? The slope is 0. So the derivative of sigma x is 0. Plus, write this down, take the derivative of the first one, which would be 2x sigma x. Excuse me. So 0 times x squared. So our answer is 2x sigma x. Set that equal to 0, and 0 is the answer for this part right here. What makes that 0 is 0. Well, this also makes 0, but it's at 0. So that's our answer to check. Second derivative. Second derivative of this is a product rule again. Okay, so the derivative of this part is 0, so we're really only taking the derivative of that, so it's 2 sigma x. What makes that 0? 0 does. All right, take this, plug it in the second derivative. Sigma of 0 is 0. Test fails, so I must come back up here and check on both sides. I put a minus 1 in here. Put a minus here, that's a minus. Sigma of any negative is a negative 1, so that's positive. If I put a positive in here, that's positive, that's positive. Oh, test fails. Okay, now let's go down here. If I check on both sides here, if I put a minus 1 in here, it's negative. If I put a plus 1 in here, it's positive. So it does change signs, so it is a point of inflection. All right, graphically, let's see what that says then. Graphically, at 0, this y value is 0. So at 0, 0. Let's see, on this side it's concave downward. And on this side it's concave upward. So that must be the way the graph looks. And that's kind of right, because what happens on this problem is the graph of x squared looks like this. And what sigma does times something, it takes the negative side and kind of reflects it. It just bends it down the other way. So that would make this true. All right, this concludes then the examples on part 1 of tape 415 about the application derivatives, finding maximum points and inflections, and sketching.